Good morning. Can everybody hear me okay?
Yeah.
You guys can hear me? Okay. Um, for some reason, I do not know why, but for some reason my computer, my Zoom setup is not showing you guys. It's not showing the faces, the people. It's just showing me a list. Oh, there it is. Wow, why did that take so long? Hello, I see Tahara, Amanda. Okay, wonderful. All right. So we are going to start with chapter 2 today. Not start with, hopefully we'll get through chapter 2 today. I'm a little bit concerned about time between this week and next week. And what I will probably do is I probably will just continue until the material is covered. If it happens to go past noon and you can't stay, you're welcome to go watch the video. I think that's a better solution than not covering the material. So I think today we'll get through chapter 2. It's more next week that I'm concerned about. And I think I mentioned it on Tuesday. If I get through chapter 2 and have some time, I will start on chapter 3 today. I just don't know if that's going to happen. I was hoping on Tuesday that we would get through more than chapter 1, but we didn't. Okay, so does anybody have any questions before we get started, whether it's over material or over what's required in D2L or anything like that? Everybody knows that your first four things are due tonight? Not 4, is it 4? Register and connect math, watch the video, take your syllabus quiz. Am I missing something? I feel like I'm missing something. I think that's it though. So make sure that you do those by midnight. And then the next thing that's due is on Sunday night, your first Connect Math homework assignment is due. And those are not listed in D2L. Those are only listed in Connect Math. So just be aware that there's assignments due every week. Most times it's due on Sundays, but there's a few times when we have tests that it's due on Thursday or Friday. So you have to keep it, you have to keep an eye on that in Connect Math. So, all right, so let's go ahead and put up the PowerPoint here. I got the PowerPoint slides up. Hopefully, just a second. There we go. Everybody see that okay?
Yes, ma'am.
Okay, thank you so much. All right, so what we're going to start talking about today, this chapter, I didn't put it up here just to save copying and pasting, but the chapter is called Frequency Distributions and Graphs. So frequency distributions are a type of table that organize data, and then graphs are, there's various types of graph, but there's 3 specific graphs that we're really going to focus on. So we're going to focus on these tables called frequency distributions right here. And then we're going to focus on different types of graphs, but the most important types of graphs that we're going to look at in chapter 2, the first one is called a histogram. And I know you would think it would be called a histograph. I don't know exactly why it's called a histogram instead of a histograph, but that's what it's called. And then the next type that we're going to talk about is a frequency polygon. And then the third one we're going to talk about is called an ogive. It looks like ogive or ogive, but it's ogive. So, and this one, ogives used to be called cumulative frequency polygons. At some point, they decided to stop calling them that. I'll explain why I think it is, but you can think of an ogive as a cumulative frequency polygon. Basically, a frequency polygon lists each category separately, and an ogive totals them up as it goes. So we'll do those, but just to kind of give you a heads up of where we're going. So let's see if I can get rid of this. All right. And we're going to start by talking about what's raw data. Well, raw data is just kind of like the word implies. It's when you go and you do a research study or a survey or something like that, and you have collected your data. You've marked down how many people answered this way, how many people answered that way. That's called your raw data. Even if you kind of put it in order or something like that, or you separate it, this many answered this way and this many answered that way. Even if you've kind of organized it a little bit, it's still basically considered raw data. So the first thing that a lot of times a researcher will do is they will create what's called a frequency distribution. And it's the organization of raw data into table form using classes and frequencies. Now, what we mean by classes are, the term classes here means like categories. So we're not talking about classes like this is a class of math. We're talking about classes as in categorizing things. So we'll be marking down which class of answers or class of numbers a participant answered or measured or whatever. And then frequencies. What does frequency mean?
How often something happens?
Yes, exactly. So how often or how much? So we'll have these different categories. Sometimes it's a category that's just a description, like we talked about on Tuesday, like hair color. So your categories might be blonde, brown, gray, red, and you have these different categories that you're marking how many people fall into these categories. But more often than not, with statistics, it's usually a group of numbers. So say you're marking down test scores. You may have a class that goes from 90 to 99. The next class goes from 80 to 89. Or you might break it up by fives. You might say, these are the people that scored from 95 to 99. These are the people that scored from 90 to 94. These are so you can break those classes up how you want, those categories up how you want, but then you mark how many people are in each of those categories. And that will get you a frequency distribution. If you have, like we were talking about with the hair color, we call that a categorical frequency distribution. So when they're saying categorical frequency distribution, that's when you just have a name. It's not like in numbers. So the first one that we're going to do is actually this categorical frequency distribution because it's easier. So you just have different categories that the people fall in. It's not a group of numbers that they could fall within. It's actually just categories that they could be in. So the categorical frequency distribution, what we're going to do first is just they're pretending or making up that there were 25 Army inductees that were given a blood test, and these 25 participants had these results. So this is called the raw data. This is before it's organized into anything. And so we're assuming, as we look at that A would have been like the first inductee and B would have been the second inductee. And they really oversimplified this because they didn't mark like if they had A positive or A negative, things like that. They just listed whether they had A, B, or O. So those are the only 4 categories that they listed. So what would we want to put for our classes or categories?
Each blood type?
Each blood type, yep, exactly. So if you look at this, I'm going to go what they have since some of you are using the notes. So they listed A, B, O, AB. I'm going to go up here, so that's not on the screen, and just kind of go off of this so you could see where that comes from. Because when you see it all filled in, sometimes you're like, okay, I see it all filled in, but I don't know where each of those things came from. So here's the categories or class. And then over here, oftentimes they'll include what's called a tally column. It's not mandatory to have the tally column, but when you're doing it by hand, it's very helpful. And you don't have to remove it. Like if you were doing one by hand, I know we're not doing it this semester because we're doing our tests online, but say you were taking like a pen and paper test, you wouldn't have to remove your tally column for your final answer. It'd be fine to leave the tally column in. And then on the other hand, you don't have to have the tally column there. So if you didn't have that, it's okay. So this is optional. But when you're doing it by hand, it's very useful. Okay, and then the last category, or the last column, is the frequency. So if you were doing this by hand, like you're going to be doing on your homework, there's no way that you could just look at the data and just come up with these. You're going to have to pull out a piece of paper, make yourself a little, make yourself a table and figure it out, and then put your answer into the computer. So don't try to do your homework by just looking at the computer. You're going to have to pull out paper and pencil and calculator and work problems out just like you were doing them out of the book. Just kind of a word to the wise. Okay, so we have, I believe it was it AB, ABO? Is that what it listed it? Is that right? Oh, no, I got the last two wrong. So in the notes, it does ABO, AB. Okay, so how do you get those frequencies? Well, you just go through and you mark down as you come across something, you mark down what category it fits into. So I look at this first recruit and he or she has A, and so I'm going to mark a tally in A. And what we mean by tally is just like tick marks. And then B is the next person, B is the next person, AB is the next person, O is the next person. And you just go through and you do that. I'm going to continue doing that. So we have two O's, B, AB, B, 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 O, A, O. And then I'm in this group right here. I have A, O, 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 A, B. I have another A, B, A, O, B, A. And you just keep marking, and typically we'll mark groups of 5. So when you get 1, 2, 3, 4, then you put a hash mark. That way when you go back to count them, it's easier to count. Does anybody have any questions on that? For some reason, I have a lot of questions
Yes.
on what the tally is sometimes. Go ahead.
It doesn't have to do with the tally. I was going to ask, so right now, do we, so what we made, is that just a frequency distribution, or is it a categorical frequency distribution? Or...
It's categorical because it doesn't have numbers in it.
Okay.
So the ones that we're going to do here in a little bit that are just called frequency distributions will have like a group of numbers here.
Okay. Thank you.
So basically, if it's a categorical frequency distribution, these are nominal. Sometimes they can be ordinal too, because it could be grades like A, B, C, D, F, but they wouldn't be like a group of numbers. Okay, so for frequency, then you just count. Okay, we tallied up 5. So our frequency for blood type A is 5. Our frequency for blood type B is 7, 9 for O, and 4 for AB, and that's it. So this column is mandatory. This column is mandatory. The tally column is optional, but it's okay to leave it in there. So let's look at their nice here. Now this, I've always been not very happy that they put this in on the first example, because this is not actually needed. This is the frequency distribution right here. So this column that they added in is kind of extra that they've added in. So what is that and what does that mean? It's not necessarily a bad thing to talk about right now. What they did over there is they did a percent. I'm going to do it differently though, because after this example, they never really talk about percents in the frequency distributions. They talk about proportions. So let's do it as a proportion rather than a percent. And you could change it in your notes if you want to. So what we mean by the percentage or the proportion is, instead of saying there's 5 people who have blood type A, we're going to say what part of the whole is blood type A. So remember, there were 25 people total. Oh, by the way, when you're doing these, when you get done and you get your numbers written down here, one way to kind of check that you didn't, completely miss something is to add these up. That you didn't miss something or double count something. This should add up to how many you had originally, of course. Okay, so we have 25 total. So if you have 5 out of the 25 that have blood type A, that means you have 20% or 0.20 that are type A. And sometimes this is more useful to the researcher than this. Sometimes they'll list only the frequency. Sometimes they don't really care about how many actual A types there were. They just want to know what part of the whole had type A. So you could say, 20% of the group had type A, or 0.20 of the group. Is everybody okay with how I got that?
Yes.
Yes.
You good? Okay. One thing I see students do a lot is divide these backwards. Remember, when you're doing a fraction like this and switching it into a decimal, it's the top number divided by the bottom number. So I actually just learned this not very long ago. The division sign is actually supposed to look like a fraction, and the top number is supposed to, or this top dot is supposed to represent this number in front, and this bottom dot is supposed to represent the number after. So this literally means I'm doing a division, or I'm doing a fraction, but I just want to put it in one line. So I'm going to put the 5 in front. Then I'm going to do the fraction bar, and then I'm going to put the 25 after. But the 5 is supposed to be on top, 25 on the bottom. So this is what you type into your calculator if you're trying to get that number. Don't do it backwards. It'll completely mess it up. I mean, if you do 25 divided by 5, you'll get 5. That doesn't even make any sense for a proportion. Got to be less than 1. Okay, so moving on to these, then if we do 7 out of 25, that would be what for a proportion? And we can cheat a little bit and go down here. But 7 out of 25, if you multiply, how I would do these if I was doing it in my head, I'd say 25 times 4 is 100, 7 times 4 is 28. So this is 0.28. You don't have to do anything in your head. You'll always have your calculator, but that's 0.28. And then 9 out of 25 is 0.36. And then 4 out of 25 is 0.16. And that matches up with these. They just wrote percent. I wish if they had done this, they would have at least put the percent signs afterwards. So is everybody okay with that, with where I got the proportions from?
Yes.
Yep, okay.
Yes.
And this is what we do. I don't know why they did percentages on this example, because the whole rest of the section, when we talk about, how it relates to the whole, we do proportions. So we do the decimals like this. Okay, so now we're going to talk about a grouped frequency distribution. As I mentioned, a grouped frequency distribution, or what we often just call a frequency distribution, is usually used when the range of the data is large. In other words, like from the smallest number to the biggest number is fairly spread out. You wouldn't necessarily use this if your numbers were real close together. So you wouldn't use it for, say, quiz scores. Quiz scores, you'd probably just, if it was a 10-point quiz, you'd probably just list how many people got 0, how many people got 1, how many people got 2, and so on. This is usually used when you have like a large range of numbers and you just want to put people into kind of similar groups, even if they didn't get the exact same score. The smallest and largest possible data values in a particular class are called the lower and the upper class limits. And then we have class boundaries. So boundaries is what we were talking about on Tuesday, where you do that kind of halfway mark between them. This will get to be really important when we make the histograms and the frequency polygons, or the histograms especially. So these boundaries are really important when we make the histogram. They don't really do us a lot of good with the frequency distribution. It's more for when we get to that graphing. And then they go into this long spiel here. To find a class boundary, average the upper class limit of one class and the lower class limit of the next class. They're just saying you go kind of halfway in between. This is a lot easier if I show it. So we'll just show it here in these next examples. Okay, but there is a difference between classes and the boundary values. The boundary values are in between the classes. So let's go look at this example over here. Oh, we have a couple more things here. The class width can be calculated by either subtracting lower class limits between two classes, upper class limits between two classes, or we can use boundaries, or you can use the upper and lower class boundary. Again, I'll show you what they mean by this. They make it sound way more complicated than it is. And then the class midpoint is just the average, like where the middle of a class is. So for instance, let's say you went from 90 to 99. In the middle of that would be 95. Actually 90. Actually it'd be 4.5. So you would have the upper and the lower, and you'd find the middle of that. Again, much easier to show once we do one. So when we get to this other one, I'll kind of point all these things out. These are they call them rules for classes in a grouped frequency distribution. Some of these are hard, fast rules, and some of them are just kind of suggestions. So I'll tell you which is which as we go. There really should be between 5 to 20 classes. If you get less than 5 classes, that's when you say, do I really need a grouped frequency distribution, or could I just list each score or each height or whatever out separately? Do I really need to group them together? And if you get more than 20, you should probably make bigger range in your classes, because it gets pretty hard to look at a table that has 20 things listed, you know, from top to bottom, or to look at a graph that has 20 different bars in it. It's very muddled and confusing. So this is not a hard, fast rule. This is a suggestion, okay? So we'll say that one's a suggestion. But we do really kind of try to stay with this. So here, this is suggested, but not necessarily always followed. The class width should be an odd number. Again, this is just suggested. The class width, meaning from the bottom to the top, should be an odd number. So if you take the top minus the bottom, it should be odd. Again, we'll do that when we do the things. Mutually exclusive, that's mandatory. Okay, so the classes must be mutually exclusive. So that means when you're listing out your classes, say we had a class that went from 90 to 94, the next class would have to start at 95. I can't have the next class start at 93 or 94, because then you wouldn't know when you were listing something, do I put it into this class or do I put it into that class? So when I, pick somebody's score on this test, I should know, where does it go? There should only be one place it can go. And so these should not overlap. They should be mutually exclusive. So that's like not overlapping. They need to be continuous. That's mandatory. So if I have, if somebody could get a 94 and the next score they could get is a 95, I have to have 94 listed and 95 listed. I have to have somewhere for that to go. Even if nobody got that score, it has to be listed in my classes if it was a possible score or a possible value. So I can't skip. So I can't say, oh, I'm going to go 90 to 94 and then nobody got a 95, so I'm going to start my next one at 96 and go to 100. I can't do that, because then if someone had gotten a 95, where would we put them? They can't go into this category. They can't go into this class because there's nothing big enough. They can't go into this class because there's nothing small enough. So 95 has no home. And so this is not okay to do. So we don't want to do that. We don't want to skip 95. Where would that guy go? The exhaustive is kind of similar to that. It just means you can't stop too low or too high. So if somebody, now this one's more based on the actual scores. So if somebody has a 99, you have to have a category that goes as high as 90, or a class that goes as high as 99. If somebody got a score as low as 50, you have to have a class that goes as low as 50. So you have to have a class that fits the very lowest and a class that fits the very highest score. And then the classes have to be equal in width. So even if it seems like it's convenient because a lot of people are within a small area, or very few people are within a large area, you can't just say, oh, I'm going to make this class width different than the other one. If you start with class widths of 5, all the classes have to be 5. So you have to stick with that as you go. So these are all mandatory. These are just suggested. All right, so the data that we're going to look at is this data, and we're not going to tally up, don't have a panic attack. We're not going to tally up all of that. That's time consuming and not good for our time right now. Maybe something on a homework, but not for right now. But we're going to record the make a table for the high temperatures for each of the 50 states. And it says we're supposed to construct a group frequency distribution using 7 classes. So when we're doing that, where would the classes go? Like, where am I going to list 7 things out?
You're on the table side, left side?
On the left side. So we're going to have 7 rows. Does that make sense? So for the classes, we're going to have 7 rows. So there's going to be 1, 2, 3, 4, 5, 6, 7 rows here in our classes. Does that make sense?
Yeah.
Okay. So 7 classes. Now what we have to do is we have to look at this data and we have to decide what range of values, or what value should I put in here for my class to make that happen. So they were nice enough to mark that 100 is the lowest value and 134 is the highest value. So if I need to go from 100 to 134, and I want to kind of split that up into 7 equally width classes of equal width, what do you guys think I should do for that? And I know the slide's right there, but so if
5.
Right, and now how do we do that though? Like, how do you know it's 5?
I was just getting it 7 classes, and 35 would be 5.
Perfect. I mean, you're doing the same thing. You're kind of thinking about it a different way, but you're doing the same thing. You're saying 100 to 134 is 35 different numbers. Well, 35 divided by 7 means you're going to get groups of 5. So the general step is you take the high value minus the low value. So in this case, 134 minus 100, our high minus our low, and that gets us 34. Now we have to be a little careful on that because this is actually 35 values. I know they're 34 apart from each other, but if we count both ends, 100, if we count from 1 to 34, that's 34. 101 to 134. If we went 101, 102, up to 134, that's 34 values, right?
Yes.
Okay. But we also have 100. So there's actually 35 different values that could go into the numbers from 100 to 134. Once we do that subtraction, then we divide it by how many there are. So we're doing the high minus the low, or the maximum value minus the minimum value. And then we take that number and divide it by how many classes we want. So we want 7 classes, and that gets us, it's 4 point something, but we have to round up. So it's 5 when we round up. So this is how wide we want our classes. This little bit right here drives people crazy on the homework. So I'm going to try to make sure that we do this real slow on this next part. When I say we want 5, we want a width of 5, we have to remember, just like up here, 100 to 134 is 34, or it's actually 35 values. We have to do the same thing over here. So our class, our first class, is going to start at 100, because that's the lowest value. And then it's going to go to what number? I want 5 potential values that could go into that first class. So if I have 5 potential numbers, that would be 100 to what?
104.
Exactly. Which is, again, as you can imagine, if somebody hasn't watched a video, they're just trying to kind of do it on their own, you'd easily say, oh, well, if it's a class with the 5, I'd do 100 to 105. That seems to make sense. But that's not how it goes. It goes 100 to 104, because that's these 5 values that could go into it. So if I come across a 100, I'll mark it in here. If I come across a 103, I would mark it in here. But there's 5 potential values, 100, 101, 102, 103, 104, that can go into that class. Does that make sense, guys?
Yes.
Okay. I know it's a little bit bothersome maybe, but as long as you can do it, that's what we need to do. So what's the next class start with?
105.
105. Again, we don't want these to overlap. We want the classes to be mutually exclusive. So this one's 105, and then and that would go up to 109. 105, 106, 107, 108, 109. That's 5 different values that could go into that category. 5, 6, 7, 8, and 9. So 5 values that could go into that next class. Now, where the 5 comes from is, and this is what they were talking about in that other slide where they got really wordy. I think class width, yeah, class width can be calculated by subtracting successive lower class limits, successive upper class limits, or upper and lower boundaries. So we haven't talked about the boundaries yet, but the limits, you notice here from 100 to 105, how far apart are those?
5.
5. That's where you get the 5. It's from the lower boundary of 1 to the lower boundary of the next one is 5. That's where you see the 5. So sometimes when people do these, instead of saying 100 to 104 here, they'll fill in like all the left ones first. So let me do it that way. So like 100, 105, next one would be, whoops, let me get my pen back to black here. So the next one would be 110, 115, 120, 125, and 130. I'm going to get rid of these numbers over here, because this was just to let us realize we were supposed to have 7 rows. It wouldn't actually be there. Okay, so what's easiest about this is you can do your 5, 10, 15, 20, 25, 30, and then you can come back in and put your upper limit. So if this one starts at 105, this one ends at 104. If this one starts at 110, this one ends at 109. This would end at 114, so I can go to 115, 119, 124, 129, and then this would be 134. Just kind of a hint if you have a little hard time with that 5 thing, or you know, the width thing. If you just do all the uppers and then fill in the lowers, or the lowers and then fill in the uppers, that sometimes helps. Everybody good so far?
Yes.
Okay, so the next thing that we're going to do, and if you're not okay, don't hesitate to say so. It's okay to ask a question. Remember, a lot of times if you ask a question, somebody else is going, oh, thank God they asked that. I wanted to know that, but I was too scared to ask. So if you are, if you have a question, don't hesitate to ask. All right, so now we have our limits. Our next step, if we were going to do this, would be to start to tally up. And again, I'm not going to tally 50 numbers, but the process would be, I'd look at my first number and, oh, there's 112. That would mark here. There's a 100 that would mark here. There's a 127 here, 120, and you would just continue that process. 134, 118, 105, 110, 109, 112, and you would continue that process until you had done all 50 numbers. Then you would count for your frequency. Everybody so good? So far, so good?
Yes.
Okay. So let me clear this all up. I'm actually just going to clear all of this, and I'll put that raw data back up as we go. So here's the raw data again. And here's what we were starting. So here's the slide that kind of describes what we did. For convenience sakes, we'll choose the lowest data value, 100. Subsequent lower limits are adding 5 like we did, and so on. And then you get your table. I'm going to just jump to this slide. So if we tallied all of those, which we're not going to tally all of them, but if we tallied all of them, this is how it came out. It came out as 100 to 104 had a frequency of 2. So there was 2 states that would have been marked in that category. There were 8 states that would have been marked 105 to 109, and so on. So what we had before, we had our group here, we would have been tallying up 100 to 104, there would have been 2 marks. This one, there would have been 8 marks.
What are the upper class and lower class limits?
So that's just the lowest and highest number. So these are the class limits, and the lower class limit for the first one is 100, and the upper class limit for the first class is 104.
Oh, gotcha.
Yeah, just literally like the lowest value and the highest value. Now they've added another column in here. So let's kind of get rid of these tallies for right now. And if you need the class boundaries, that's like what we did on Tuesday. So this is important. Again, it seems like, why are we doing this? When we're doing the frequency tables, it really seems pointless. But when we do the graphs, it's not pointless. So these class boundaries are very helpful when we make our histogram. So if you need those boundaries, how do you find those boundaries? Well, you go halfway between an upper class limit and then the next lower class limit. So in other words, what is halfway between 104 and 105?
102.
Oh, you're doing a midpoint.
Oh, sorry.
Between like this class and
104.5.
yeah, 104.5. You were thinking midpoint. So midpoint of this class would be 102. Actually, be 102 point. It'd be 102.5 actually. Is that right? 100. Let me write this down first. So this would be 99.5. Yeah, it'd be 102.5. So hold on a second. 99. So to find the midpoint, you take the boundaries and you average them. So 99.5 plus 104.5, and then you average. So this would be 14. Spin it by hand. You get 204. Is that right? 9, 10, 14. Yeah, so 102 would actually be the midpoint of this. Sorry, I made that way more complicated than it needed to be. My brain wasn't wrapping around that correctly. So it's not 102.5, it's 102. So the midpoint of this class would be 102 because it's the average between the upper and the lower. And you can average these or you can average these, you'll get the same number. So what would be the boundary for this next one? It's going to pick up where this one left off, so 104.5, and then it's going to go up to the next category, which we want to go halfway between 109 and 110. So that would be 109.5. So the boundaries just fall right in between the upper for this one and then the lower for this one. So halfway between 104 and 105 is 104.5. Halfway between 109 and 110 is 109.5. And we'll use these when we get to the graphs. Does anybody have any questions on that?
Could you explain the midpoint thing again?
Yeah, and I'm sorry, I kind of flubbed that up, which made it more confusing than it needed to be. To get the midpoint, you can either average these two numbers or you can average these two numbers. And usually the classes are easier to average because they don't have the 0.5s in them. So the midpoint is just going to be the average of those. So let's not use the boundaries because that's more complicated. So 100 plus 104 and then just average it. So that's 204 divided by 2, so the midpoint is 102. Does that make sense?
Yes, and it's just the first class or
Well, you could find midpoints for all the classes.
for all the classes.
Yeah, so the midpoint for this one would be 107. The one for this one would be 112. You could do it for all the classes.
Gotcha.
And the midpoints we actually use when we do the frequency polygons. So that's needed when we do the frequency polygons. The boundaries are needed for the histograms and the midpoints are needed for the frequency polygons.
Can you explain the boundaries one more time?
So when you're looking at the classes, so let's just erase these like we hadn't even done it yet. The first one's a little confusing because it goes under the first class. But if you've got your class listed out and you're trying to figure out what the boundaries are, you're going to look, again, I often will just look at this one first and then fill it in. So what is in between 104 and 105? Like halfway in between them.
Okay, I see now.
Does that make sense? So 104.5?
Yes, ma'am.
And then you start adding 5 to it. So this one starts where this one picks up. So these do kind of, they don't overlap. Well, they kind of overlap. I mean, 104.5 and then we start at 104.5. So where this one ends, this one starts.
Okay.
And so then this one goes up 5, 109.5. And then this next one picks up where that one left off. So
So
109.5 is halfway between 109 and 110.
Okay. You just subtracted 104.5 minus 5 to get the 99.
Yep, exactly. And so then I have to go back and fill this out because these all go up by 5s. So what would be 5 under 104.5 would be 99.5. It's also like half a half of a value down from 100.
Mm-hmm.
So you're taking this class and you're like bumping it down half and up half on each side.
Gotcha.
So 105 gets bumped down to 104.5, 109 gets bumped up to 109.5. It'll make a lot more sense why the heck we do that when we do the graph.
Thank you.
Okay, and so then the last thing that they kind of threw into this table is we could also, instead of talking about just the frequency, we could talk about relative frequency and we could talk about cumulative frequency. Let me see what this next table has on it. So for the cumulative frequency, what we mean by cumulative, think about what the word accumulate means. So if you say to somebody, you've accumulated a lot of things. Oh, sorry, I'm talking and trying to write at the same time again. Accumulate. So if somebody has if you say to somebody, you've accumulated a lot of stuff, you're telling them that they've collected a lot of things, right? Accumulate. You've accumulated a lot of hours at work, means you've built up a lot of hours that you've worked. You've accumulated a lot of books, means you've collected up a lot of books. Does that make sense? What the accumulate?
Yes.
So that's, and accumulate comes from this word cumulate or cumulative. So what we're talking about here with a cumulative frequency is, instead of just saying what is in that class, we're going to say what's in that class or less. So when we talk about cumulative frequency, let me get rid of some of this junk over here. So when we're talking about cumulative frequency, this right here, I want to list how many that are 104 or less. So how many data values did I have that are 104 or less?
2.
2. So this number is going to be the same between the two columns. The frequency for that first class and the cumulative frequency for that first class are the same. But now, this next one, I want to write down how many are, this next class is 109. So how many are 109 or less?
Is that 10?
10.
10.
Yep. So now I look at everything that's in the 105 to 109 plus everything that was already in the 100 to 104. So 8 here plus the 2 that I already had. I have 10 values that are 109 or less. Then what about the next category? This would be how many are 114 or less.
28.
28.
Yep. And there's a couple different ways you can do it. I think most people, once they kind of really start to get it, they'll just go, they'll write down this 2, and then they'll go 2 plus 8 is 10, 10 plus 18 is 28, 28 plus 13 is, but you could also go back and add up these. So like 18 plus 8 plus 2 gets you 28. 13 plus 18 plus 8 plus 2 gets you, what is that, 41? And then 7 plus 13 plus 18 plus 8 plus 2, or 41 plus 7 gives you 48. And then add one more, you get 49, and then add one more and you get 50. So again, what does this, I know we skipped a few, but what does that number right there mean? What does the 50 mean?
The whole data set?
So it's the number that are what or less?
All 50 states or less?
Right, but what's the
34.
134? Remember, these were degrees, so we could put that in. That might be helpful. So this is the number of states that have their high temperature of 134 degrees or less. So all 50 have 134 or less. There's nothing above that. We've reached the end, and that means that there are 50 states that had 134 or less. Let's do one more. So what does the 48 mean? That's the number that are
124.
124.5 or less.
Yep. And you could say 124.5 or 124, because there won't be any half values. I mean, there's no, you can't actually have one of your measurements be 124.5. So if you say it's 124 or less or 124.5 or less, they're both accurate. On your homework, I can't remember, now that you guys said that, gave that answer that way, I can't remember if it asks you to do the 124 or the 124.5. Those have to kind of follow what it says. If ever you guys are having problems on the homework, as far as like you don't know what form you want the answer in, look at the example problem. So you know how there's the example problems you can click on? Well, actually in chapter 1, there's not very many example problems. But anyway, click on the example problem, and however they give the answer in the example problem is how they want you to give your answer. So that's kind of a little helpful hint. Okay, so let me just put this up here really quick because this is their nice pretty version of it. So here's their nice pretty version of what we just did. So 2, 10, 28, 41, 48, 49, 50. All right. So that's everything with the frequency distributions. We did categorical, we did grouped, we did cumulative, we did the proportion. We kind of hit on everything. So now we're going to get into section 2.2. And we're going to talk about the graphs.
Hey y'all, so you guys were really responsive to like my weight loss transformation. A lot of you guys were asking, what do I eat in a day? So if you want to go from this.
Can somebody turn off their mic? Somebody's got something going in the background. Okay, awesome. So we're gonna now go to speaking of stuff going off in the background, my phone rings on cue. Okay, so the next thing that we're going to talk about in 2.2 is the graphs. Okay, so we have the 3 most common graphs are that histogram that I spoke of, the frequency polygon, and the cumulative frequency polygon, which is now called an ogive. And so those are the 3 that we're going to learn to construct. Now, again, if we were doing a face-to-face class and or I was having you go in to take a face-to-face test, you would have to hand create these graphs. Obviously, since we're doing this, you know, the testing online, I can't make you do that. So on the test, it's going to be, you know, which of these is correct. So I would practice, you know, when you're doing your homework, practice actually doing them by hand. Because it'll help you practice and find out like the little details and little pieces that need to be in place. But on the test, it's going to give you several to choose from, and you have to pick the right one. Okay. Any questions on that before we actually start doing them? Okay. The first one that we're going to do here, the histogram, we're going to use that data that we just used. And for a histogram, we are going to make a graph that displays the data using vertical bars of various heights to represent the frequencies. So let's kind of mark this over here. When you're looking at a histogram, we've got a bar graph. This in general is a bar graph. And then the frequency polygon in general is a line graph. And then the cumulative frequency polygon is again a different type of line graph, but it's a line graph that does the cumulative frequencies. So instead of just saying how many are in each category, it says how many are in that point or less. Okay, but this is a type of bar graph, this is a type of line graph, and this is another type of line graph. So this histogram is a graph that displays the data using vertical bars. So it's very specific with a histogram. Your bars are supposed to go this way. They're not supposed to go sideways. They're supposed to go from the bottom up. They have to be vertical graphs. And then the class boundaries, the ones that we were fiddling with and trying to figure out where they came from, those little half numbers, those class boundaries go along the bottom here. Okay, so let me, let's get to the, it says we're supposed to construct a histogram using, to represent the data for the record high temperature. So this is the same data that we had before. So I'm going to put their nice little version up here. We're going to make a histogram off of this data. And again, that's just the same one we just did. Okay, so we're going to take, and along the bottom, we're going to put the class boundaries. So what's the lowest number I need here along the bottom? Remember, these are the boundaries, not the limits.
99.5.
99.5.
Yep. So, oh, my tablet. Okay, so 99.5. And then what would be my next mark?
104.5.
104.5. So I do 99.5, 104.5, and then I just keep adding 5 to it. So I already have 104.5, so I do 109.5. And then I do 114, and I keep going until I get to my 134. So 114.5, 119.5, 124.5, 129.5, and then lastly 134.5. Hopefully you can read that. I know it's a little bit messy when I try to write small with this pen. Okay, so that's going to be my horizontal axis. It's like my input. What do you think I put along the side here? Frequencies. So this is like my, kind of like my X, and this is kind of like my Y. It's not exactly, because the X would be a single input value, but it's kind of similar. So what is I have to look at this. What do I have to get up to? What do I
18.
need? I need to get to 18. If you want to, you could go by ones, but I would say for something that goes up to 18, I'd probably just go by twos. I don't necessarily want to make 18 tick marks over here. So I'll just do 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, these are supposed to be evenly spaced. I know this looks a little bigger than the other ones. If this was, a true, nicely published graph, I would want these all to be evenly spaced. And could I do on my side, could I do like 2 and then go to 6 and then make my next one 8 and then make my next one 11? Would that be okay to do?
No.
No.
See, these have 4 between them. Then 6 to 8 has 2 between them. 8 to 11 has 3 between them. I can't do that. Each successive number has to be the same distance apart. So if that's 2, this has to be 2, etc. You have to keep that up. And you might think, well, of course, I know that. I would never do that. But what people do is they try to take the numbers that are there, that are listed, and put those on the graph. So they'll come over here and they'll be like, okay, I need a 1. So they'll mark a 1. This is what I'll see happen. They'll say, okay, well, my lowest number is a 1. So I'll mark that here. And then my next number is a 2. And my next number is a 7. I'll see that. My next number is an 8. And then they'll have a mark for 13. You see, that mistake is what is made, and we do not want to do that. That is not the correct way. You want to see what's my lowest, what's my highest. Really, really try to start at 0 if you can, and then just make sure you have it high enough that you can get the highest value in there. So far, so good for everybody? If anybody has any questions, feel free to shout it out. Okay, so these are your boundaries. This is your frequencies, and then what you do is you come in here and you make your bars. So I have 2 values that are from 109 to 104.5, and you want to span that entire class to show that they could be anywhere between those. Usually in the book, they'll color these in, but if I try to do that, it's just going to look ugly, so we'll leave it alone. So what do I do with my next bar?
From 104.5 to 109.5.
And how high up will it go?
8.
8. So I do a bar that goes from 104.5 to 109.5 that goes up to a height of 8. And then I just continue. So my next one would go to a height of 18. I'm going to go all the way up here, over, and down. It's actually pretty decent for trying to do it on the tablet. And then I do this next one from here to be at 13. And you notice all these bars are touching because they span the entire width of the, from a lower class boundary to the upper class boundary. So 13, and then we're going to be at 7, and then we're going to be at 1 and 1. And that's a very visual representation of what's going on. Most people, you know, visually, they can pick up on this even better than this. They can say, oh, okay, so almost all of them are somewhere between 104 and 124. There's just a few below that and a few above that, but the bulk of it here, the highest category was here. So this visual representation, your brain really likes the graph because it can pick things out and patterns and such out a lot faster. Is everybody okay with how we did this?
Yes.
Good so far? Okay.
Yes.
So I'm going to go up to the next thing that we're going to do, which is the frequency polygon. But I'm going to leave this on here for just a minute. So, because I want to show the relationship between the frequency polygon and the histogram. So when we do a frequency polygon, it's a graph that displays the same data. So it doesn't change what we're displaying, it just does it a different way. By using lines that connect points plotted at the midpoints. So it's going to be a line graph instead of a bar graph, and we're going to use the class midpoints instead of the boundaries. And then those midpoints have to go along the horizontal axis. Now, you could go off of the graph that you already had, but it gets a little bit messy. So my recommendation would be start over. You know, write down what your midpoints are and start this over. But just to show the relationship between the two, a frequency polygon for this is going to put a dot where all the centers of the tops of these bars are. So this is what a frequency polygon is going to look like. It's going to look like this red version here. So instead of having bars, it's going to have lines, line segments. Now, the little bit tricky part about this is you notice this dot isn't at the end of either of these boundaries. And also, the other trick is this has to come back, and I'll explain how, but this has to come back and attach to the x-axis, and this has to attach to the x-axis. So if you try to just go off of what you had, these numbers down here get a little tricky. So again, I would recommend you start over again. Just recreate a new graph and relabel it instead of trying to make it work off of your old one. Okay, so let's do that. Get rid of this. All right. So if we were going to make a frequency polygon for this data, what does it say I need to put along the bottom? What goes down here? Before it was boundaries.
Temperatures?
It will be the temperatures, but what numbers are we going to put down there?
The midpoints.
The
There you go.
midpoints.
There you go. So this is going to be the midpoints of the temperature. You're right, it's temperature, but it's the midpoints of the temperature classes. Okay, and then over here, we're still going to do frequency. Okay, so we're still going to do frequency over here, and over here, down here, we're going to put the midpoints. We don't have the midpoints listed. So what do we need to do?
Calculate them.
You have to figure them out. I mean, these aren't just there, and you probably don't want to just do them in your head. So you have to go over here and actually calculate them. You can try to kind of squeeze them in somewhere. I just usually just put them on the end. So I'll just write the midpoint over here so that I have it as I go here. So what's the midpoint? We talked about this before. What's the midpoint of 100 to 104?
102.
102. And that's, again, we get that by taking 100 plus 104 and then averaging it. So that's 204 divided by 2, which is 102. And a lot of times you can kind of see it. Like, okay, well, halfway between 100 and 104 would be 102. If you can see it, you can do it that way. But the technical way is to do the average. So 105 and 109, these are now going to go up by 5s because remember our class widths were 5. So halfway between those are the average. 105 plus 109 over 2 would be 214, which is average is 107. You guys okay with those? What would the next one
Yes.
be? So 112, there you go. And now, again, we're just adding 5. So 102 plus 5 plus another 5 would be 117, 122, 127, 132. So you can keep averaging these if you want to, but now that we've established that pattern that it's just going up by 5, because that's the class width, you could just write those down. And where do these go?
On the bottom,
On the bottom. There we
on the
go.
x-axis.
And I'm going to tell you, leave a little space here if you're doing this on your notes or on a separate piece of paper or whatnot. Don't put 102 all the way over here at the edge because we're going to have to fill something else in there. So kind of scooch it over a little bit. Leave yourself a little room. So we're going to do 102, 107, 112, 117, 122, 127, and 132. What about our frequencies?
Are they the same?
The same. We still have to get up to 18, right? So we'll just do 2, 4, 6, 8, 10, 12, 14, 16, 18. Again, these really should be evenly spaced. I know it's a little ugly on my writing pad here, but those should be evenly spaced and they should go by equal intervals. So go by, once you start going by 2s, make sure you keep going by 2s. Okay, so where am I going to put my first dot on my graph? Like what would be my X value and what would be my Y value?
I would assume
102 and 2.
There you go. You'd do 102 and then at 2.
Yes.
Okay, so this is now like your X and this is like your Y, right? So my X is 102 and I have 2. That midpoint, I have a frequency of 2. And so then 107 would be at 8. 112 would be at 18. Oop, gotta erase this junk that's up here. Okay, so 112 would be at 18. 117 would be at 13. Then 7 and 1 and 1. You notice I'm putting them right above the midpoints. Don't put them in between. The 102.2 should go right above the 102. This should be right above the midpoint at 8, right above the midpoint at 18. And then I connect them. So I put little line segments between them. And I'm almost done with my frequency polygon. So flashback to geometry. I hear so many horror stories about people's geometry experiences. Hopefully yours wasn't traumatic. But flashback to geometry class. What's a polygon?
Isn't it a shape with more than 3 sides?
Yeah, 3 or more sides because a
And it's
triangle would.
closed?
and it has to be closed. So if you look at this, I've got 1, 2, 3, 4, 5, like a 6-sided polygon here, kind of, but it's not closed. So to be a polygon, the reason they call it a frequency polygon, this has to be closed up. And right now I've got holes in it. So what I do is I come back and I go the same pattern. So remember, these were going by 5s. I have to follow the same pattern. I have to come back 5 and put a mark here. So I'd be 97 since these were going by 5s. So from here to here, you have to subtract 5 to get that. What's really awkward about that is sometimes it'll go into the negatives when negative values weren't even possible. So like you'll have maybe 2, 7, 12 or whatever. If these were just, say this didn't have the 100 in front of it, then I would have had to come back here and been at, a negative number. I would have had to be like -3. So sometimes this will go into the negatives, which seems weird, but you still have to keep the same pattern. So that'd be 97. What would I have up here?
137.
137. And now you're saying again, why the heck would I put a 97 and 137? They weren't midpoints. Well, we're going to indicate that. We're going to say, if there was a prior category that had a midpoint of 97, it would have had nothing in it. If we had a further midpoint past 132, that would have been nothing in it. There's a category beyond 130 to 134 that would have a midpoint of 137 that does not have any values in it, and you connect those. And now this is a polygon. It uses the x-axis as its bottom segment here, and then it uses the other segments and it's all closed in. And that's our frequency polygon. People forget to do this all the time. Just remember, you shouldn't have that hanging around up there. Oh, and these are called anchors, by the way. So we're anchoring it to the x-axis. So we anchor it on both ends, basically, so it doesn't, kind of imagine you don't want it to float off. So these are midpoints. Put your dots right above the midpoints, anchor on each end with a consistent pattern of numbers. Any questions on that? Okay, hopefully it's not because you're stunned into silence. All right, let's see. I want to show theirs just because, again, it's always a little prettier than mine. So this is what their beautiful graph looks like. Okay, so that, it's the same one we just made, just their pretty version. They decided to go by 3s over here. But again, we decided to go by 2s. It doesn't really matter as long as you keep it consistent. And then, but here along the bottom, they did the 102, 107, and then they anchored it back and anchored it forward. I don't like on this that it doesn't show what these are. They should have marked this is 97 and this is 137. I don't know why they got lazy and left that off. I don't know if it was an oversight or. Okay, so I'm going to clear this out. Does anybody need anything from here before I clear it out? All right. So the next thing that we're going to do is we're going to look at how to do an ogive. An ogive is oh, and I forgot to mention, let me bring this up here again. Let me put their pretty version of their histogram up here, because I didn't explain this and I said I would. So why do we use these boundary values down here instead of just putting like 100 to 104, 105 to 109? Why do we do that? Well, if we tried to put, instead of the boundary values here, we tried to put the class limits, and we say, okay, this is 100, and then this one's 104. Or wait, no, I don't want 104 because the next one is actually 105. That gets a little confusing. What do you put? Do you put the lower values or do you put the upper values? So even if I put the lower values, if I were to mark this with a 100 and a 105, which of these bars contains 105? Do we know when we look at that? If we said this starts at 100 and this goes to 105, where does an actual 105 value go? Does it go here or does it go here? I mean, the way we graphed it, where did it go? Did it go into the blue one or the orange one?
The orange one?
The way we graphed it, it was the orange one, because we did these boundaries, which made it clear that, and this is going to erase my numbers, but I'll write them back in. It made it clear when you do the boundaries, this is 99.5, this is 104.5. So that made it clear that if I had a 105, it definitely goes here because that's above 104.5. So it eliminates that problem of those numbers that are right on the cusp between the two classes. It eliminates that issue of which one did I put it in or where is it at. You'll see it done. There's all kinds of times you'll see it published with the actual class numbers instead of the boundary numbers. But then you have to kind of either guess or they have to tell you where did those cutoff values go. Did they go into the lower boxes or did they go into the upper boxes? So the correct way to do it is with these boundary values so there's no confusion. So I know, again, for instance, let's say I had a 120 value. I know that went where? Did it go into the yellow or did it go into the red?
Into the red.
Into the red, because we use the boundary value of 119.5. So I know anything above 119.5 got put into the red. If I had a 119, it would have gotten put into the yellow because it's below 119.5. So there's no question about where each value got placed within the histogram. That's why we use the boundary values instead of the class values. Okay, so now back to the ogive. Let me get rid of this. So here's our value again. We have our limits, our midpoints, our frequency. I chose one that didn't have the boundary values in it because, let's see, actually, that'd probably be more helpful. Just a second. Let me get rid of this one, and I'm going to put this one up instead. Okay, so we don't really need midpoints for a cumulative frequency polygon. So remember, now we're going to do a cumulative frequency polygon, which is called an ogive. And here's the rules for an ogive. For an ogive, you're going to make a graph that represents the cumulative frequencies for the classes in a frequency distribution, and the upper class boundaries are on the horizontal axis. Okay, so it's the cumulative frequencies, and we put the upper class boundaries on the horizontal axis. Okay, so let's do that first. Let's put the upper class boundaries first. So what's the first upper class boundary? Here's our class boundaries. What's that?
99.5.
That's our first lower class boundary. So you've got the right idea, but we want to pick this one.
104.5.
Yeah. Now I'm going to do something later. You're going to be like, that's what I said. For right now, I'm just following the rules here. Put the upper class boundaries. So I'm going to put the 104, but leave a little space over here. Okay. Leave yourself a little space between 104.5. Okay. So then what's the next upper class boundary?
109.
109. So we put these upper class boundaries, 109, 114, 119, 124, I'm just going to get rid of this for right now. I want my whiteboard back. Okay, 129.5 and 134.5. Okay, so there's my upper class boundaries. So the upper class temperature boundaries. All right. Now it's supposed to be a cumulative frequency polygon. So what do I need to do to this table before I make my graph? What do I need on the table? Like for the polygon, I needed midpoints. What do I need this time?
The list of cumulative frequencies we did earlier.
Yep. So we need those cumulative frequencies. So we'll fill those back in. This was 2, and then we added 8 to get 10, 18 to get 28, and so on. This was 41, 48, 49, and 50. This should be your total, by the way. That last number should be how many you have. So we had 50 states. That's why we got 50. Okay, so last thing before we can start plotting any points, if I'm plotting cumulative frequencies, what numbers do I want to put along the side over here? Will 2, 4, 6, 8 up to 18, will that work now?
That would be a lot of tally marks.
That'd be a lot of tally marks, because what do we have to get to?
50.
We have to get to 50 now. So this is, remember, cumulative. So this right here has to be, writing sideways is not good, but this has to be cumulative frequencies along the sides. So I've got to get up to 50. So I don't want to go 2, 4, 6. I probably want to go by 5s or 10s. Let's go ahead and go by 5s. So I want to do like 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. This should be nice and even. You know, if you were doing it by hand, some graph paper would be good, but probably don't need that. And then is this going to be dots or bars? You guys remember? We're going to put dots on here for the cumulative frequency, or are we going to put bars like the histogram?
Dots, because it's a line graph.
Yeah, it's like the frequency polygon. It's a line graph, so we just want to put dots. So what am I going to put at 104.5?
2. 2.
2. Yep, you got it. And then at 109.5, I'm going to put not 8, because I'm not doing the frequencies, I'm doing the cumulative frequencies, so I'm going to put 10. So this means there's 10 values that are 109.5 or less. Then I'm going to do all the way up to 28. And then up to 41. Again, what that means is there's 41 values that are 119.5 or less. Let me make a little note of that. So we want to come down here. That means that there's 41 states with 119.5 degrees or less. Because there'd be all of these states. The 13 that were here, the 18 that were here, the 8 that were here, the 2 that were there. So 41 total have 119.5 or less. What are my last couple dots? What would I have at, actually I have 3 left, 124.5. Where would that be at?
48.
48. And this is going to be pretty hard to discern, but I'm supposed to be 48 and then 49 and then 50. So they should go up just a little bit. And then I connect that. And they should be little segments, not curves. Sometimes it starts to look curvy, but So quick question. What can an ogive do as far as from one point to another? Can it go downward?
Wait, my computer just like froze, so I haven't been able to see what you've been doing.
Okay, where did you freeze up at? What were we at? Had we done these yet?
Yeah, you were doing the cumulative thing.
Okay, so we did the cumulative frequencies. You okay with
Mhm.
that?
Mhm.
Okay, and then we just plotted them. So we plotted 104.52 and then 109.5, 10, and then 114.5, 28, and so on.
Okay.
So what's the only thing that graph can do?
It has to go up.
Okay, so an ogive can only go up. That's what you said. Is that true? Can it only go up? And the answer is almost. You're almost right. It can only go up or stay flat. So if you had a category that didn't have any in it, so like let's say that this one state that was 125 to 129, let's say it was actually in the lower category and we had, 13.801, then we would go 49, 49, 50. So it could go flat, but can it come downward?
No.
No, because we're accumulating the numbers as we go, right? So if we're just accumulating numbers, you can't have less states that had 124.5 or less than you did that had 119.5 or less. We're accumulating, we're adding on as we go. So this can only go up or potentially stay flat if you had a category that didn't, like a class that didn't have anything in it. So that's one way to recognize an ogive. An ogive can only go up or stay flat. It cannot come downward. So one last thing before we're done, and you're going to say, wait a minute, the person who said, I'm sorry, I didn't catch you said that said 99.5, come back here and put that 99.5, but what are we going to put for the value there? How many data values are 99.5 or less?
Zero.
0. So we are going to put 99.5, but that's our anchor before our actual first value. So we're saying there were 0 states that were 99.5 or less. So you actually do use that lower class boundary, but it's your anchor.
Do you dot it or do you plot it or do you just start it from that point?
You plot 99.50 and then that's your first line segment. I usually
Okay.
go back and do it at the end though, because otherwise it's really easy to get this other stuff messed up. So I'll do all my upper boundaries, plot them, and then I'll be like, okay, now I got to come back and anchor it. Now, would it make any sense to anchor this ogive over on this end? Would it make sense to do a 139.5 and anchor this down?
No.
No, because then you're saying there's 0 states that have 139.5 or less, right? That doesn't make sense. We have 50 that are 134 or less. So this does not make sense. We cannot anchor it on the right, and thus it's not a polygon, which is why I believe they stopped using this term, this cumulative frequency polygon, because an ogive isn't a polygon. You can't anchor it on the side, so it's open, so it's not a polygon. So I think that's why
What
they
is
stopped
the-
using this name and started using this one. Go ahead.
What is the yellow line explaining?
Oh, I was just saying that this point right here, like if you wanted to, analyze what this point means, that point means that there were 119 go over here. There were 41 states, because it was this point, 119.541. So there were 41 states that had 119.5 or less for their temperature. That's what that point means, because it's cumulative. So you can't say there's 41 states with 119. You have to say 119.5 or less. Are you okay with that now?
Yes, ma'am.
Okay. So it's really important when you're talking about the ogives to remember that all the points are that much or less. Otherwise, there'd be no point in doing it. Otherwise, we'd just be, we'd stop at the frequency polygon. Okay, so I'm just going to show you again their nice, pretty version. So here's their version of what we just did. But it's the same, the same thing. I think ours was pretty good. That's pretty pretty. Okay, so the next thing that we're going to talk about are relative frequency graphs. So let me clear this off. What we have done the bulk of this section, or this chapter actually. We've covered histograms. We've covered the frequency polygons, and we've covered the ogives, which are the relative frequency polygons. But for all of these, what we listed along the side were the frequencies, or the cumulative frequencies. Okay, we always listed the actual number of things in each category. But do you guys remember way back to the blood types, how else could we look at the frequency of something? Do we have to give the actual values? Did we have to say there were 5 people that had type A? What else could you do?
Say the percentage.
Yeah, like the percentage or the proportion. Perfect. Okay, those are called relative frequency. Okay, so we can have a relative frequency histogram. We could have a relative frequency polygon, and we can have relative frequency ogive. How does that differ? Well, if you looked at the graph itself, like the actual bars and the actual line segments, it doesn't look any different. But what it records on the side, like on the y-axis, is the percentages or the proportions. Okay, so you would have the percent or proportion of the whole on the y-axis. So instead of saying there's 5 that have blood type A, you would say there's 20% that has blood type A. Now our book, you can do percent, that would be totally appropriate, like in everyday practice. Our book always does the proportions. It always gives, instead of saying 20%, it would say 0.20 or 0.2, just so you know. So here's the slide for this. I know some of you are trying to fill in your notes here. So here's the slide for this. If proportions are used instead of frequencies, the graphs are called relative frequency graphs. So again, relative frequency histogram, relative frequency polygon, relative frequency ogive. Relative frequency graphs are used when you would rather have the proportion of the data values, if that's more important to you, than the actual number. So it's more important to you to know that there's 20% that have blood type A than it is to know that there were 5 in your group. So we're going to practice this with the histogram, and then I'm going to show you the other ones, but we're not going to actually do them all because they're very repetitive of what we just did. So I'll show them to you, and if you want to come back and watch the video later and fill in your notes or whatnot, you can. But I want to make sure we get through chapter 2. But just so you know, we've done almost everything. What we've done is the bulk of the hard work. We know how to make a frequency table or frequency sorry, I lost my words here. We know how to make that frequency distribution. Couldn't come up with the word distribution. So we know how to do that frequency distribution now, that table. We know how to make the 3 types of graphs, and we know what a relative frequency is. We just haven't graphed it yet. So we've done the bulk of the work. So let's go to make a relative frequency histogram. Let me get the right slide here. Are you guys okay with me getting clearing this out? Is there anything anybody needs? All right, going once, going twice. Okay, so it says that they want us to now construct a histogram, a frequency polygon, and an ogive using relative frequencies for this distribution. Thank goodness they gave us some different data, because the states thing was getting a little boring. So they gave us something different here. So let's analyze this a little. It is miles that 20 randomly selected runners ran during a given week. So what does 55.5 to 10.5, 1? What does this mean? What does that first row mean? If somebody said analyze that or describe it, what it means, what would you say?
Is that one runner?
Okay, one runner. One runner what?
You ran between 5.5 and 10.5 miles.
Okay, so one runner ran between 5.5 to 10.5 miles. Perfect. So that's what that means. So when you look at this, we know that, but from the frequency distribution, that this means one runner was in that class, and then we have 2 runners that are in this next class. So this would mean 2 runners ran 10.5 to 15.5 miles. Do we actually know what they ran?
No.
No. One thing about if you're never given the raw data, if you're only given the frequency distribution, you actually lose a little bit of information, because we don't know if those 2 runners ran. We know that they were probably going to the nearest mile because the boundaries are at halves, but we don't know if they ran 11 miles, 12 miles, 13, 14, or 15. So when we say 10.5 to 15.5, that means they either ran 11, 12, 13, 14, or 15. But we don't know which. We don't know if both runners ran 11, if one runner ran 12 and one ran 15. We don't know. So when you group it up like this, you do lose some of the original information from the raw data. Is everybody good with what this all means, though? You're good with reading that table?
Yes.
Yes.
Yeah, okay. Again, let me know if not. And
Did they always give you the frequency, or?
they either have to give you the frequency or they have to give you the raw data so that you can calculate the frequency. So it could be like the other one where they just gave us all 50 states and we had to do it ourselves, or they might give it to you like this.
How do you find the frequency again?
You calculate up your class boundaries, like you figure out your class boundaries, and then you literally have to go through the data and tally it up. So you have to say, there's one in this category, there's one in this category. You just have to keep marking until you've got them all marked and then count them up.
Oh, okay. And I wouldn't be able to do it here because they didn't give us a raw data.
Right. We can't do a
Okay.
tally. Well, I mean, we could do a tally, but we wouldn't know. Yeah, we don't have the raw data. So,
Okay.
but yeah, they've already tallied it, listed the frequencies, and gotten rid of the raw data. We don't know that info anymore. So, but if they gave us the raw data, we would have had to, tally it up. So as they tallied it, there must have been 1 runner here and 2 runners here, 3 runners as they counted there, 5 in the next category, and so on. So as they tallied it up, this is what they got, and then they wrote it out, and then they got rid of this info and they threw out the raw data and we don't have it anymore. Is everybody okay with that? Like where they got this from?
Yes.
And we don't, it's okay, because all we're doing is we're going to do these graphs, and we don't need all that. We don't need the raw data for the graph or anything. Okay, so now we're going to do, like I said, we're going to just do the histogram, but then the frequency polygon and the ogive would follow in a similar manner. But if we do the histogram, what are we going to put? That's that bar graph thing. What am I going to put along the bottom here of the histogram?
Boundaries for the miles.
Okay, so this first number here would be 5.5, right?
Yes.
And then 10.5. And then 15.5. If all they give is the classes, you would have to figure these out. So if they had said, you know, 6 to 10, you'd have to figure out 5.5 to 10.5. Just depends on what they give you. In this class, in this situation, they were nice enough to actually give them to us. 20.5, 25.5, 30.5, 35.5, and 40.5. But I'm supposed to make a relative frequency polygon, or relative frequency histogram. So over here, do I want to mark 1, 2, 3, 4, 5? Because the highest number is a 5.
Yes. No.
No, what do I need? I need those
Proportions.
relatives. Yep, I need those proportions or relative frequencies. The proportion or relative frequency means it's pretty much the same thing. So I need the proportion or the relative frequency. So how many runners were there?
20.
20. So how many, or what proportion is 1 out of 20? That would be 0.05. So 1/20th is the same as 5/100ths, which is 0.05 or 5%. We have to keep doing that all the way down. 2 out of 20 is 10%. So 10% of the runners ran from 10.5 to 15.5. Just keep going. So this would be 0.15. Would be 3 out of 20. 5 out of 20 is 0.25. 4 is 0.2. 3 is 0.15 again, and then 2 is 0.10 again. So these numbers, I'll do yellow here. So these numbers are the relative frequencies. So now that we have that, now we're ready to label our y-axis, because this is supposed to be the relative, so hard to write sideways on this, relative frequencies. So if this is supposed to be the relative frequencies, what do I need to get to? Like, what's my span here? I really want to start at 0 if I can, but how high do I need to go?
25 is the highest.
Highest is 25. So this has to get up to 0.25. So again, I could go 0.01, 0.02, 0.03, 0.04, but that's kind of a pain. I could go by 2s. I could go by 3s or 4s, but honestly, the easiest is probably to go by 5s, right? 0.05, 0.10, 0.15, 0.20, and 0.25. Now, that's not because those are the only values that were given here. It's because we had to go from 0 to 0.25, and going by 0.05 was convenient. So even if there had been like a 0.18 or a 0.16 7 or something in here, we still probably would have marked it the same. So far, so good. What are we gonna do for bars now, guys?
Dots.
You
Dots for if it was the frequency frequency polygon, we would have marked midpoints and we'd put a dot if it was a frequency polygon.
to be the columns.
But we want the histogram is the bar graph. So this one for the histogram, this is the bar graph. So we're going to do a bar that goes to 5% for this first column. What about the next one?
To 0.10.
And that spans all the way from 10.5 to 15.5. It goes up to 0.10. Histogram, these bars have to touch because we're indicating that it could be any place between those in that range of values. Or that span of values. Then we're going to go to 15. This one is very symmetric. We've got 15, and we've got 25. That's the first time that we don't just jump by a 5. And then we've got 20 and 15 and 10. And so this is now a relative frequency polygon. If I wanted to do just a frequency polygon, I would have gone 1, 2, 3, 4, 5 on the side. But since I want relative frequency, I went 0.05, 0.10, 0.15, like 5%, 10%, 15%, so on. What do you guys think of that? Anybody have any questions on that one? Let me ask one really quick question because we haven't done this. If I were to do the cumulative, this gets crazy, cumulative relative frequencies, what would that total up to? If I started totaling up the frequencies, the relative frequencies, what would be my final total every single time?
1.
1. It would total up to everything, right? Let's do that really quick. We won't do the graphs, but let's do the cumulative frequency so you can kind of see. So the cumulative relative frequency, I'd get 0.05 for my first one. And then to the 0.05, I would add 0.10. So my next one would be 0.15. Then to that, I would add another 0.15. So I'd be at 0.30. Then I would add 0.25. So I'd be at 0.55. Again, every time I'm just adding on the next category to what I already had for a total. So I'm at 5%, add 10%, puts me at 15. Add 15%, that puts me at 30. Add 25%, that puts me at 55. This would be 75. If I added 20%, add 15%, I'm at 90. And then I add the final 10% and I'm at 1. That has to total up to like 100%. If we were doing just a cumulative frequency, it would have added up to 20. Does anybody have any questions on that? And I'm going to show you what the graphs look like, even though we're not going to do it from start to finish. Hold on a second. So this is the one we just did. I erased it, but this is the one we just did. That's the histogram, where you have the boundaries along the bottom, and then you marked it from 0 to 25%. Then this is what the frequency polygon would have looked like. So we mentioned before the dots. It would look, it's still got that same general shape. It still starts low, comes up, comes down, but these dots are at the midpoints. So they would be literally, this dot right here would be the top of that bar right there. And then that dot came from the top of that bar. But we mark the midpoints along the bottom. So instead of 5.5 to 10.5, we average those and put 8. And then don't forget to anchor at the beginning and the end. I don't like how they're being lazy about marking the. They really should have a 3 here and a 43 here. I don't know why they aren't marking those, but. And then, last but not least, I have a cumulative frequency, relative cumulative frequency ogive. So cumulative and relative frequency. So that's these numbers that we had here. The 5, they marked 5%, then 15, then 30, then 55, then 75, then 90, then 100. And along the bottom, we go back to doing the boundaries again. What do you guys think?
So what's the difference between the ogives and the frequency polygons? It's just the y-axis is cumulative.
Yep, that's it. So over here, instead of marking each category separately, which means it could kind of go up and down and up and down, we add them up. So this one, instead of having like this frequency polygon, has 5% and then the 10%, the 15, 25. This ogive has these cumulative values. So it has 5%, then a 15%, then it has the 30%, and it just keeps going up until it gets to 1. Does that answer your question?
Yes, ma'am.
Okay. So the last thing that we're going to cover in 2.2 real briefly is just some different distribution shapes. Let me get these both up here at the same time. So these are just some kind of general shapes that you can have, and I'm going to mark which ones are the most common. So some of these we'll talk about, but the ones that you're going to hear again are right skewed and left skewed, and uniform a little bit, but then bell-shaped. We will talk, once we get to chapter 6, like the whole rest of the book, we talk about bell-shaped curves, bell-shaped distributions. So bell-shaped, as you can see, it's very symmetric, kind of like the one we just did with the runners. It's very symmetric. It peaks up in the middle, and then it slopes down nice and evenly on each side. So it kind of ends up looking like, oh, the Liberty Bell. Okay, so it's kind of got a bell shape to it. It has to be, we call it bimodal, because it only has one biggest value, one biggest peak here. And then it's symmetric on each side. This one looks like it's pretty perfectly bell-shaped. Even if something is just sort of bell-shaped, we can call it approximately bell-shaped. This one, they called it uniform, but this actually isn't perfectly uniform. What would it be if it was perfectly uniform?
Like just a solid rectangle with
Exactly.
no altering heights.
Exactly. It would just be flat. They would all be like the same height if it was truly uniform. So uniform means like every category has the same number in it. So perfect. Okay, so this one, you can kind of see why they call it a J shape, because it kind of looks like a J. And it's kind of like a left side of a bell-shaped curve. You get, you start at the left and you get bigger and bigger and bigger and bigger, but then it never goes back down on the other side. So that's called a J shape. And then for obvious reasons, this one's called the reverse J shape. So it looks like this one, but it goes the other way. So it starts high and it just keeps going down, 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 down. And that's called a reverse J shape. These two you really won't hear much after this chapter. I don't think they ever talk about it again, to be honest. And then right skewed, left skewed. These are important. And we do talk about these more later. When you're looking at this, if somebody said describe this graph right here, and I'm pointing at the right skewed one. Describe this graph right here. Would you come up with the word right, or would you look at that and think that that was left something? And if so, why? Why do you think students want to call that left something? It's okay to be wrong. We're not doing any homework or test or anything.
Are you talking about the reverse J-shaped graph?
No, I'm talking about the right skewed here.
Oh, you're saying why they would say it's left?
Yeah, why would people want to say this is some sort of left something graph?
Well, because the graph is going to, like, the higher points are going towards the left, but when you're looking at whether it's skewed left or right, you need to look at the tail of the graph.
Perfect. So when you look at this, you look at this and you think, students look at this and they say, well, the bulk of the data, there's more data up here on the left side. Wouldn't this be called a left, a left something graph? That's where most of the data is. But the skewedness means, being skewed means being kind of led away. If somebody, skews your opinion, means you're kind of being led away from where your bulk of your ideas are. So being right skewed means the bulk of the data is to the left, but there's these values down here that are pulling the average away from the bulk of the data. So let's say this was a test and these were test scores. This would mean, a lot of people got scores down here. Maybe these are C's and B's, but you have a few people that got A's and really high A's. Those people would pull the average up away from where kind of the middle of the class is. So like you said, think of this kind of like an animal, and you have to look at where it tails off at. So if this is like the body of the animal, the tail is the direction that we call the skew. So this is called right skewed, and this one is called left skewed, because this would be, if we think of test scores again, think of most people in the class did really well. You got, maybe these are the people who got 95 to 100. These are people who got 90 to 94, and so on. But what about these people down here? What did they do to the class average? The people that did poorly.
You did?
Yep, it would skew it downward. It would pull the average down, right? So a left skew pulls it down. So these people that tail off to the right here, these few people, even though there's not as many of them, it pulls the average down from where the middle values would be. Right skewed and left skewed can also be called positively skewed and negatively skewed. Those mean the same thing. So left skewed and negatively skewed is the same thing and right skewed and positively skewed are the same thing. And then again, these ones aren't going to be common, but if you run across this one, it's called bimodal. Bi meaning two, and it just means it has two different classes that are kind of the peaks. It doesn't come to a single peak like a bell shape does, or even a reverse. Even the J shape and the reverse J have a single category that's the highest. Even the skews do that too. Here you have those are your highest. So those are unimodal. This one is bimodal because it has two that are the tallest. And then a U-shaped, I'm always kind of slayed why they call this U-shape. If you go back to here, this is a J, this is a reverse J. To me, that should be a reverse what?
Bell?
Yeah, it looks like a reverse bell, doesn't it? If you could picture looking at that upside down, like looking at the white part graphed instead of the blue part graphed, it would look kind of like a bell shape. So this is like a reverse bell when you get that U shape. So it goes down, it's like a valley with the peaks on each side instead of like a mountain like the bell shape. So those are just some general shapes. I know we're at 12. If anybody needs to go, you are welcome to go, but I'm gonna finish. That way, if you need to come back later and watch it, you can. I do want to say one thing before people leave, if you have to leave because it's noon. When you're doing your graphing on your homework, be really, really cautious when you're graphing something. if it has the axes labeled, say this is 50 and this is 60, and you're trying to plot something, whether it be a histogram or a dot, because you have to do it on the computer, you have to put like where you want your dot to be. If the value is say 53, make darn sure when you graph that you don't go past halfway between 50 and 60. If you try to graph 53 here, it's going to count it wrong, because 53 should not be past halfway between 50 and 60. Does that make sense?
Yes.
Everybody good with that? So if it had a, if it had a 55, you would want to try to make sure that, your 55 was right between 50 and 60. But if it's 56, 57, 58, 59, you better get that up above half. If it's a 58 or 59, it better be past half and closer to 60. So be really cautious on that. That's the one thing that the computer will definitely count wrong if you do that. If you put something past half that shouldn't be past half, or something before half that should be past. So hold on just 1 second, and we're going to get into section 2.3 and 2.4. Now 2.3 and 2.4 are not as long as what we've done. Again, we've done the bulk of it. We're just going to zip through kind of some different types of graphs, and we're going to talk about what are called, hold on a second. Oh, scatter plots. We're going to talk about scatter plots. I would say worst case scenario, we should be done by 12:30 if you can stick around. I need to take a break for 2 seconds. I'll be right back. So we're going to start off with bar graphs when I get back. I will be right back. Sorry about that. I have a teenage son that needs to leave for work in 30 minutes. He wasn't awake yet. Okay, so our types of bar graphs, this is considered a bar graph. And remember, our histograms were a type of bar graph. But what is different about this? Why is this not a histogram? I mean, it's a bar graph, but it's not a histogram.
The columns
Because
on
the bars
side.
are horizontal.
Yeah, good. I think you both said the same thing at the same time. So the bars are going sideways instead of up and down, right? So this is a bar graph, but it's not a histogram. This one just has categories: walk, train, trolley, how did you get to work? And then it just lists. And it's okay for a bar graph to go horizontal, but not a histogram bar graph. If it's a histogram, it has to go up and down. This one here, this is called a Pareto chart. Big fancy name. All it means is, if it's a Pareto chart, it just means it's a bar graph where they went from biggest to smallest. So you notice this, they organized it from auto, bus, trolley, because auto had the most, then bus had the next. So a Pareto chart just goes biggest to smallest. And they usually have these touch, but the point of them touching, there's really like not a lot of point to it touching, because with a histogram, you touch them because you're supposed to be spanning all those values. Here, it's just, I mean, it's just categories, so it doesn't, really matter if you touch them or don't touch them. But anyway, that's called a Pareto. The next one that we have here is called a time series graph. What is this? Kind of looks like a frequency polygon, but what makes it not a frequency polygon?
There are no anchors.
There's no anchors. We know this isn't a frequency polygon because it's not anchored. And then also, so that's the first kind of really big tip off. The other thing is, these are not midpoints. These are just actual values. So they're saying at noon, it was 41 degrees. At 1 o'clock, it was 45 degrees. At 2 o'clock, it was 43, whatever. Those aren't midpoints. Those are just time increments. So in order for it to be a time series graph, there has to be a passage of time along the bottom. And the passage of time could be days, hours, minutes, seconds. It doesn't matter. It just has to be some sort of passage of time. There's no anchors, but there needs to be a passage of time with some sort of thing recorded across that time. And that's just called a time series graph. One that I know that you're familiar with is a pie chart. The one thing that I will ask about on a test about a pie chart, obviously you can't really, you know, make one when you're taking an online test. I can't really ask you to make a pie chart, but I think it's important that you know, if you were making this pie chart, how you would figure out these degrees. Like, how do we know how big to make this piece of the pie? And so let's say we were looking at this data. I might give you a chart that says married, widowed, divorced, single, and then over here, the frequency. So let's say this was a poll of 200 people. So there would have been 100 married, 10 that were widowed, 54 divorced, and 18 single. Or I'm sorry, not 18, but 36 single, for a total of 200 people. Okay, so this is what I would give you. Okay, and my question would be, how many degrees in a pie chart for any one of these? So if I said for divorced, how many degrees would you make in the pie chart for divorced? Actually, let's change that. Since I have it marked in the graph, I have the singles marked. So let me put single. So how many degrees in the pie chart for single? How would you figure out this degree for the single people? Does anybody know how to do that? What would be your instinct on that?
Dividing that by 200.
Would that be
Okay, so divide it by 200. So divide what by 200?
The amount of singles, the frequency.
Okay, so the 36. So you'd say 36 out of 200. And that's where they got the 18%, right? 0.18. Remember, I just made this up. They didn't give us this. I just like made it up to fit what they had. Okay, so 36 out of 200. And that's where you get the 18% from. Is that how many degrees it is? Is that 18 degrees of your circle?
Yes.
don't
Would-
you need
Go ahead.
do you need to find the 18% of 360?
Yes. So if life was nice and a circle had 100 degrees in it, which sometimes you're probably like, that would be really nice if a circle had 100 degrees in it. We know how to split 100 up into halves and quarters and such really easily. But, you know, at some point, somebody decided a circle has 360 degrees. So we don't need 18% of 100. We need 18% of 360 degrees. So you have to multiply it by 360 degrees to get the number of degrees. So you're partway there with the 18%, with the 0.18, but you have to go one step further and figure out how many degrees that is. So if you were making a pie graph for this, your single people would have 64.8 degrees in their pie. So this right here would be 64.8 degrees. What do you guys think? That makes sense? This is a very, very likely question on the test. And it'd probably be the only thing I would ask you about a pie chart. So you need to remember to take the frequency and divide it by the total to get that percentage, but don't stop there because there's 360 degrees in a circle. Oh shoot, what did I just do? There it is. So you have to take that one extra step. Also, if you like proportions, doing like the cross multiplying, you could also do 36 out of 200 equals X out of 360 if you want to, because you're trying to switch it to the 360 degrees. So if you're somebody who really likes setting up a proportion and cross multiplying, you can do this too. So 200x equals whatever 36 times 360 is and solve that out. So you can do it this way too if you like. Okay. The next thing we're going to look at real quick is a dot plot. So a dot plot is a statistical graph where each data value gets plotted as a point or a dot above the horizontal axis. One thing that's nice about a dot plot is it not only shows how the values are distributed, but it shows extremely high or low values, and it also actually keeps every piece of the data. So let's say we had this as our original data set, named storms in different years. In other words, like in one year there were 19 named storms, and named storms, we're really familiar with named storms in Houston. We're talking about, you know, like Harvey had a name, something that gets big enough to have a name. So one year there were 19 named storms, another year 15. And what you would do to make a dot plot is you would just put all these possible values along an x-axis, and you just put a dot. So right here, this 19 is one of these two dots right here. So it would be that dot right there. And then that 15, that would be that dot right there. So you just list out, you know, the lowest was a 4 and the highest was a 28. So you make a scale that gets everywhere from 4 to 28, and then you put a dot for each of the values in there. It's kind of nice because it sort of looks like a little bar graph, but you still have all the little data values each have their own little dot there. You don't lose anything. If anybody has any questions on anything, holler, you know, just give me a shout. The next one is that we're going to talk about is stem and leaf. Let me get this cleared out. And what we do for stem and leaf, I always thought stem and leaf were kind of interesting or kind of unique. What we do with the stem and leaf is you use part of the data value as a stem and then the rest of the data value as a leaf, and you plot those out. So what the heck do we mean by that? Usually it's data values that have like a tens and a hundreds, or a tens and a ones place. So usually our stem is the tens value. And then our leaf, or our leaves, are the ones. So if I wanted to record 25, I would find a 2 in the stem, and then I'd mark a 5 in the leaf. So I've got to get my stem set up first. The lowest value I have here is a 2. And let's see, what's the biggest value? Does anybody see anything bigger than a 52? 57. Okay. So I have to go everywhere on my stems from a 0 in the tens place up to a 5 in the tens place. All right, so those are my stems because I have from 0 something to 50 something. And then I go through, and each one I put the ones value as the leaf. So 25 would be marked here with a 5. So this means 25. 31 would be marked like that. That's my 25, my 31. My 20 would be marked here with a 0. 32 would be marked there. 13, there's 10 and 3 for 13. 14 would be beside that one. 43, etc. Okay. Now, the only thing when you do this on your homework, they ask you to do it as an ordered stem and leaf. So when all is said and done, after you fill these in, you have to go back and put them in order. So like you'd put the 0 before the 5 and so on. So let me show you what this one looks like with it all ordered out. So here's what we were starting, is this version, the unordered. But when you're all done, they like you to put them in order. And that's called an ordered stem plot or an ordered stem and leaf plot. It's kind of nice. Again, you can see there's mostly 30s. 30s is the most common, then 40s. 20s and 50s are fairly common. 10s and 0s are fairly uncommon. So it's sort of like a sideways bar graph using numbers. The only thing that they don't talk about here that you might run across in your, or you do run across in your homework, is if you're trying to compare two different data sets, they'll put them to the side of the stem and leaf. So let's say you had another data set. This is an outpatient testing center. So say you had a different outpatient testing center with, with different data. Say it had a 15 and a 27 and a 31, and you wanted to plot it. Let's do a different one here, say 24. So if we wanted to plot that, this might be clinic 1 would be on this side, and then you would put clinic 2 on this side. So you'd put 15, there's the 10 and the 5, 27, 31, 24. And people don't usually have a problem with it being on the left side. That's not usually the problem. It's the order that messes them up. So if I'm going to put it on the left side, that it reads backwards. So this is 10 and 5, so this is 15. 20 and 7, that's 27. 24, 31. But should this be, if I was going to order it, should I have 27 and then 24? Or should I have, should I flip these? What do you guys think? What do you guys think? Should we leave it or should we flip it?
Leave it.
It seems to make sense. I mean, the 4 is before the 7, right?
Right.
Yeah. You don't. You flip it around, actually. And the reason being, you're supposed to have the smaller values close to the stem. So like here, 2, 0 is closer than 2, 3 to the stem. And so here, 2, 4 is closer to the stem than 2, 7 is. So the bigger numbers are supposed to be further away from the stem. So like the 6 is out here, so the 7 should be out here. So yeah, that really bothers people though. When they're doing their homework, they'll be like, I had all the right numbers, but you've got to list them completely backwards, 24, 27, and get bigger as you go out to the left. I know it's weird, but does it make sense now? Is everybody okay with that?
Yeah.
Okay. Again, there's maybe a question or two on your homework. The bulk of your homework is 2-2, where you're doing all those graphs and stuff. There's just kind of a few questions on each of those different types. They'll throw out a couple different questions. Read this graph, tell me what that point there means. And they're pretty straightforward. Let me clear this out. We are up to 2-4. And the last thing that we have to talk about is paired data and scatter plots, which we'll actually come back to these in chapter 10, but that's quite a ways from now. But just the general idea of what a scatter plot is. Scatter plot and dot plot to me kind of sound similar. Maybe I'm crazy and they don't to other people, but I always would get mixed up the names for a scatter plot and a dot plot. So a dot plot is where you put those dots up above, like the named storms. A scatter plot is where you put them on the plot, kind of like at XY values. So in this case, your scatter plot is a graph of ordered pairs. So it's different than a dot plot because a dot plot doesn't have ordered pairs. It just has single values. Like there were 19 hurricanes. There were 25 hurricanes, or 25 named storms, 19 named storms. Here you actually have like an input and an output. You have an X and a Y. And then you just plot those. So if you look at this data set, it says, here's the number of accidents in a 10-year period. Draw a scatter plot. This is a strange data set, but what the X is supposed to be is the number of bicycle accidents in a year, and then on wet pavement. So the number of wet bike accidents. So the number of accidents that occurred on bicycles when it was wet out. And then they plotted that against the number of wet bike fatalities, which means they died of a bike accident on wet pavement. So this year there were 376 accidents on wet pavement, and 5 of those were fatalities. And so that's what this up here means. And then all they did here is you'll find that a lot of the data in this book is very, very uplifting data. But and I say that sarcastically. So down here, what they did is they just plotted that. So they plotted 376, 5. That's probably this one right there. And then they plotted 650, 20. So 650, 20 is probably that one. Then they graphed 884, 20. Actually, that's probably the 884, 20, and this was probably the 650, 20. And they just plot those out. And then you can see a pattern developing that as you had more accidents, you had more fatalities, which only makes sense. But sometimes they're not quite that obvious. Sometimes, you know, you're trying to see if there's a relationship between two different, an input and an output value that's not obvious, and you're trying to see is there some sort of pattern or relationship between the two of them. Does anybody have any questions on that? I have one more example of this, but other than that, that's the last of what we need to do. So you guys okay with the general idea of a scatter plot? All right, I'll take your silence as no questions. So let's go. This is my other example that I have. This one, you have number of absences and then your final grade. And lo and behold, they don't have this one graphed, but lo and behold, as the number of absences gets higher, the grade goes down. So if you graph this one, instead of going upward like that graph, this graph, the points tend to go downward. As you have more absences, your grade goes downward. So higher absences, lower grade. And so what that's called in general, put this up here, is if you have data that is generally trending upward in a line, we call that a positive linear relationship. So the accidents one was a positive linear relationship. So it's kind of in a line and it's kind of going up and it's going upward. If it's kind of in a line and it's going downward, we call that negative linear relationship. If it looks just very scattered, just like, you know, somebody threw a bunch of, somebody just, you know, splattered water on a wall or something like that. That's, we'd say no relationship. And if you see a pattern developing, but it's not linear, you call that a non-linear relationship. So there's a relationship between the X and the Y. It's making this pretty distinct curve, but it's not linear. So this is positive linear because it's in a line. So it's sloping upward and it's a line. This one's sloping down and it's a line. And this one, there's a pattern, but not a line. And then if it's just very scattered and you can't see any kind of development going on, then you say there's no relationship or very little relationship. And that's all I have. Does anybody have any last questions before we call it a day?
What did you say the pattern that's not a line is called?
It's called a here, let me write it. So this one right here is called a positive linear relationship because it's in a line. And then this one would be called a negative linear. And then this is a non-linear.
Okay.
So there's a pattern, but it's not a line. So that's a non-linear relationship, and then this is no relationship. Logan, come here. Anybody else have any other questions?
Did you say the videos on the textbook are those grades, or if we like watch these and do the homework, that still counts?
Yeah, no, you don't have to watch the videos in Connect Math if you don't want to.
Okay.
If you're okay with, with this, which, we're spending, 2.5 hours on these, they're probably much more in depth than what the videos in the Connect Math are anyway. So yeah, no, as long as you can do your homework, you're fine. The videos aren't for grades in Connect Math.
Okay. Thank you.
Only the homework sections. Anything else? And if you come up with anything else, don't hesitate to email me. Also, don't hesitate to shoot me. You'll notice when you're doing your homework, there's like a ask your professor or ask your instructor or something link. That like sends me a link in my email that shows me exactly what problem you were working on, what the numbers were and everything. So if you have a question, your homework, you're welcome to do that. You have to remember though, I'm a person. You're going to have to, you're going to have to send it to me. I'm going to have to see it. I'm going to have time to answer it, get it back to you. So your first line of defense is probably to look at the example or, have it work one out for you or something like that. And then if you can't figure it out, then shoot me an email and ask me for help. Just because those other things are immediate, not because I don't want you to ask me a question. So first homework is due on Sunday night from Connect Math. It's chapter 1 and all of chapter 2. So that's 5 homework assignments. Chapter 1 is 1 homework assignment, and then there's 2-1, 2-2, 2-3, and 2-4. So don't forget, don't start working on that at like 8 o'clock on Sunday night. You'll be kicking yourself if you do that. Get a start on it as soon as you can. All right, have a good day, and we will see you next Tuesday.
Thank you.
Thank you.
Thank you.
There's your faces. I don't know why it's not showing you guys on the other screen. So I'm glad you stuck with me, and we'll see you next week. Take care. Bye-bye.
Bye.